Baby. All right, good morning, lads and ladies. Welcome back to Honors Calc 1. Today is our review for Exam 1. And remember, Exam 1 is going to be this Wednesday, which is our next class period. So we really want to be prepared. Today is the day to ask any questions from homework problems or study guide problems that have been frustrating or worrying you. Let me see if I intended to post an announcement for you guys this morning. You can see behind me here that I've moved into a new home. Everything is pretty chaotic right now, but the internet guy came by just an hour or two ago, so I'm not using my phone anymore. That's a big step up, and we should have a pretty smooth lecture here. I do want to check and see, because I intended to post. No, so you guys still need the class announcement. Yeah, this announcement for the exam. So right now I'm going to go ahead and post the instructions for our exam. These are the same as they are for my other Calc 1. Isn't any time specific stuff in here. There is, yeah, we want to change this to 10:45. Okay. All right, so the exam is this Wednesday during class. Before class starts, I want you guys to make sure you've got Zoom installed on your phone and Google Chrome and HonorLock installed on your laptop or whatever PC computer you use at home to do stuff. A few minutes before the start of class, I want you to log into a Zoom meeting that I'm going to post a link for here. If you can't log in exactly at 10:45, actually I'm going to have to change this to 11 because yeah, my other class will still be working at 10:45. So right at 11, I want you guys to click and log into a Zoom meeting that's going to be posted here, but you're going to do it on your phone. Once you're into Zoom on your phones, I'll have you set your phone like balanced up against a coffee cup or something on your desk so I can see your hands, your paper, all that good stuff that we need to see to proctor. Once we are all happy with that setup, you're going to log into Canvas using Google Chrome, and you'll go to the assignments thing here and you'll click on Exam 1. That'll get HonorLock running and get you started on the test, and then you can just roll through it. While you take the test, use pencil and paper to answer each question to the best of your ability. True, false, and multiple choice questions, all you got to do is click the right answer. For the free response questions, you got to do two things. You got to write the problem down on your paper and solve the problem on your paper, and then type your final answer in the box. On your paper where you're writing down the problem and showing your written work, please write just one problem per page, like one problem per side. You can do, front and back, that's fine. But please just one problem per side, and please, please, please make sure you number the problems. And don't forget to write your name at the top of at least one of the pages. You're going to roll through the test like that until you're done. Once you finish the test, you're going to scan your written work and submit it to the assignment titled, scan your written work here. Quick note on those free response problems, you got to type your final answer in the box. If you just have your written work, the written work is what I'm grading, okay? But if I don't have an answer typed in the box, I cannot give any credit. It's a hard and fast rule, and it needs to be there to prevent a certain kind of cheating that I saw a lot of last semester. So you got to type your final answer in the box. You got to write your workout on the paper. And of course, they have to match. That's important. And then after you finish the test, you'll submit your written work, and then that will be it. If you do have any questions, hit me up and we'll take care of them. So go back and read this announcement. Make sure you're really clear on everything there. If you do end up with any questions, let me know. Otherwise, the rest of the class here today is your guys' day. We are reviewing for the test. So any problems you guys want to see from the homework study guide, just start typing them into the chat, and we'll get moving. So, if you want to see homework 5, problem 3, just go ahead and type that into the chat. What's today? The 8th? It's the 8th, yeah. And reviewing is all we're doing today, no new material. Okay, I can take a look at some study guide problems. I won't solve the exact problems that are there, but I'll do my best to come up with a similar one that focuses on the same sort of stuff. While I'm doing this, please everybody look at whatever stuff you want and type the problems in, because we've got a whole period here. Just type them in the chat and I'm going to solve them in the order they come in, to be fair to those who submit them. Did this thing really sign me out already? God damn, Cengage. It's not a Cengage sign-in without at least one kickout and bad request. All right. Oh, right, wrong class. Here you guys are. So study guide numbers 5 and 9. Let's take a look at 5 here. Yeah, so this is a squeeze theorem problem. I'll do a similar one. So I'd like to find the limit as x goes to 0 of x to the 4 times the sine of pi over x, which is similar to that study guide problem. The idea here, if you look at this graph or the graph from the study guide problem in Desmos, you'll realize it oscillates very quickly near 0. I can look at it. I was doing some things like this with my earlier class. Look at just pi over x. Zoom out a little. Right, here's just sine of pi over x. And you see as we get closer and closer to 0, it oscillates really, really fast. So that's the problem. And if you change this to cosine of 9 over x, it's going to look very similar. Right? All of these things have this problem. So the challenge here certainly the sine of pi over 0 is undefined because pi over 0 is undefined. And indeed, the limit as x goes to 0 of sine pi over x on its own, this does not exist due to rapid oscillations. So somehow, maybe this limit doesn't exist. Or the only other possibility is that somehow this x to the 4th like calms down this really bad behavior that we see here. And that's, if you remember back to the problems like this that we did in class, that's exactly what happens. So if you multiply this by x to the 4, and we scale our y-axes, 1 to 0.1, or even a little smaller. And let's do something like this. So you see, even though we still have these pretty wild oscillations, they are actually being tamped down. And the trick is to recognize the boundary functions. These, I'll come back to this in just a minute. But for the moment, what we're trying to do is figure out the limit as x goes to 0 of this thing, which definitely, to me, looks like it's probably going to be 0. But it's hard to tell because you've got these waves like oscillating back and forth really fast. And we know that that happens anytime you have like a sine of 1 over x or a cos of 1 over x, anything that's sine or cosine of something which is undefined at 0. The way we attack this is with the squeeze theorem. Remember the way the squeeze theorem works? We have to find a function that bounds my function from above, a function that bounds my function from below, and then I take the limit of those outer guys. And if those outer guys both go to the same place, then the inner guy has to go there also. If we were looking just at the problem piece, on its own, sine of pi over x, as badly behaved as he is, he's always bounded between -1 and 1, right? I mean, my scales here are really bizarre. Right, but he's always stuck between -1 and 1. And that's true for any sine function and any cosine function. If you just have sine of some stuff or cosine of some stuff, then it's always true that -1 is less than or equal to the sine of that stuff is less than or equal to 1. Because of the way sine is defined. Sine is defined as a y value on the unit circle. The unit circle has radius 1, so it never gets bigger than 1, never gets smaller than -1. And our goal here is to make my function show up in the middle, make this thing show up in the middle. Is everybody comfy where this inequality comes from? Just the range of the sine function being -1 to 1. So in order to resolve these two challenges, we want to make our function show up in the middle of this inequality. That will let us apply the squeeze theorem. So the way to do that is to multiply through this inequality by x to the 4. And when I multiply through by x to the 4, I do get my function in the middle. And the question is, of the functions that are now on the outside, can I take their limit? And do they have the same limit? So now we take the we take the limit of the functions on the outside. So lim x to 0, -x to the 4. And you calculate that, and lim x to 0 of x to the 4. All right, what is this? What is the limit as x goes to 0 of -x to the 4? Who can help me with that? Yeah, 0, right? This function, x to the 4, is continuous at 0. You can take that limit just by plugging in. And x to the 4 itself also goes to 0. So the policeman behind me is going to 0. The policeman in front of me is going to 0. That means I am also going to 0. So I say, therefore, lim x to 0, x to the 4, sine pi over x must be 0 also by the squeeze theorem. Is everybody comfy with this? Are there any questions about how this is working? You being good, Bubble? Sorry, that's my dog, not you guys. Okay. If there aren't any questions on this, I know these are somewhat complicated, so you're sure there's no questions? We can take a look at number 9. That's 6. This is 9. This is also a squeeze theorem, right? But this time we're going to infinity. So it's the same sort of thing. You need to set up an inequality bounding the functions. Something like this. Looking for the limit as x goes to positive infinity. So e, yeah, I'll do e to the negative x over sine x. Same sort of thing, right? You know that the limit of sine x as x goes to infinity doesn't exist. It just bounces back and forth between -1 and 1. You know, this piece goes to 0, but 0 times dne, who knows? Could be anything. So exact same thing, squeeze theorem. Start with -1 less than or equal to sine x less than or equal to 1. This implies that negative e to the negative x is less than or equal to e to the negative x sine x. It's less than or equal to e to the negative x. Now, we'll take the limit as x goes to infinity, right? Because that's where this limit is of both of the boundary functions. Let's see what we get. Again, both of these are 0. As x goes to infinity, e to the negative x goes to 0. So negative e to the negative x goes to 0. And as x goes to infinity, e to the negative x goes to 0. We just said that. So these guys are both 0. These are special limits, remember? These are limits that we learned back in section 2.6, limits at infinity. So where were these? Or even before this. Yeah, so here along with the arctan limits, we had e to the negative x. Where is it? Maybe it was after this. Where's this bullshit? Oh, maybe it was before that. That's a little different. Let's see. I'm not seeing this right now, but I know that we, yeah, there it is. There it is. There it is. Yeah, right. As x goes to negative infinity, e to the x goes to 0. And I broke this down into like 4 different cases for us with the arctan stuff. So e to the negative infinity is 0. That's the easiest way to think of that. So as x goes to positive infinity, e to the negative x is e to the negative infinity, which is 0. And now these two force the middle guy to be 0. Yes, you absolutely should know the graph of e to the negative x. This is a graph you should know well. Right? This is one of those graphs we start teaching back in college algebra. You know, it has this horizontal asymptote. This is y equals e to the negative x. You should know the graph of e to the x also. Arctan x, all these basic graphs. I'm definitely assuming you guys know, right? These are all things that y'all should know well. Okay, so that's 5 and 9. We want to look at homework 2, number 44. Okay. This is another limit at infinity thing. This one requires some more careful algebra. This is not a squeeze theorem thing. So let me write this guy down and then we'll see what we can do with it. We're sending x to infinity in the expression square root of x plus 2x squared, all divided by 5x minus 1. The trick to these limits at infinity with kind of ratios of algebraic functions is to ask, what is the fastest growing term? So here, I've got an x downstairs. That's the fastest growing term downstairs. Upstairs, I have an x and a 2x squared, but they're both under the square root. So sort of the fastest growing terms upstairs is like a square root x plus 2x squared, which is kind of like x, and downstairs is just the x. So the idea is upstairs I have an x squared, but it's under a square root. I can't simplify this algebraically at all, but I know that if you take the square root of something that grows at the speed of something quadratic, the result is something that grows at the speed of x. So sort of x is our fastest growing term, both upstairs and downstairs, or the bottom and the top both grow at linear speed. That's how we would say their growth rates are both like big O of x. I'm going to divide top and bottom by x. That's the game. We divide top and bottom by the fastest growing term. This is that renormalization trick. So I'll multiply up top by 1 over x, and I'll multiply downstairs by 1 over x. And this is how we divide top and bottom by x. Of course, when we do this, we have to think of everything as being in parentheses. And the last sort of trick to making this go, this is a little bit clever algebra-wise. You have to rewrite the 1 over x upstairs as the square root of 1 over x squared. All right, like this. Good so far? So now upstairs, I can combine the two square roots. Downstairs, I can distribute. Upstairs, once I've combined the two square roots, I will also distribute. I get lim x to infinity, 1 big square root of x plus 2x squared times 1 over x squared. And then downstairs, when I distribute, I'll have 5 minus 1 over x. Right, 5x times 1 over x is just 5. And then 2x, and then minus 1 times 1 over x is minus 1 over x. God damn it, man, I just can't get away from this fucking phone calls tomorrow. Scam likely. All right, now we distribute under the square root upstairs. 1 over x squared times x is 1 over x. 2x squared times 1 over x squared is 2. So we do all that algebra to get here. As x goes to infinity, what does 1 over x do? Who can help us with that? At 0, we have a vertical asymptote, but this is something else. It's related to a horizontal asymptote. Yeah, it goes to 0. All right, so remember we have this theorem. This is an important theorem. This is what most of this stuff hitches on. said if r is a positive number, then the limit as x goes to infinity of 1 over x to the r is 0. And it's coming from not a vertical asymptote, but a horizontal asymptote. If I think about like 1 over x squared, all of those graphs kind of look like this. Right, this is the graph, say, of y equals 1 over x. So as we wander off further and further to the right, we are getting closer and closer and closer to 0. In other words, if you divide 1 by a bigger and bigger and bigger number, you get a smaller and smaller and smaller number. If you really want to write this out, you can write this as 1 over square root 1 over infinity plus 2 divided by 5 minus 1 over infinity. And then ask yourself, what should 1 over infinity be? If you take 1 over something enormous, that should be very small. So this is 1 over infinity should be 0, square root of 0 plus 2 divided by 5 minus 0. So you get root 2 over 5. These limits at infinity, you might think they're not super important now because we haven't used them when we talk about differentiation rules. But believe me when I say they're going to come back in a big way at the end of class, and then they're going to come back in a huge way in Calc 2. So it's worth taking the time to learn these and understand them, but don't confuse them with the other limit rules that we've got, right? Limits at infinity are kind of a little special. Most important things, make sure you remember this rule. Make sure you remember the e to the x and inverse tangent of x stuff. And make sure you remember the renormalization trick, which is the trick that we used here. That's really all you need for limits at infinity, at least in Calc 1. I'll zoom out a little bit. I guess we should show the last few steps probably. Is there anything else in particular we want to see here? Any questions on this guy? And again, kind of like Tahara was saying, this can come from knowing the graph, right? If you understand the graph of these sort of functions, you'll realize, yeah, they all do go to 0. It's kind of a... We divide top and bottom by whatever the largest power is, or whatever the fastest growing term is. So if we want more practice for these, come back to section 2.6 here. My advice. Look at some of the example problems they have in section 2.6, like example 3. This is a really straightforward example using that renormalization trick. You see the fastest growing term upstairs is the x squared. Fastest growing term downstairs is the x squared. So we divide top and bottom by x squared, right? They divide the top by x squared and they divide the bottom by x squared. And that simplifies this. This is the so-called renormalization trick. And then, you know, they're very verbose about this. They give the limit to each piece here, but you don't really need to do that. You just say, oh, the 1 over x is going to go to 0. The 2 over x squared is going to go to 0. All of these pieces that have an x downstairs are going to go to 0. So you're going to get 3/5. That's the quick way. But they've got lots of examples like this, and I would recommend looking at some of these if you're feeling a little nervous about limits at infinity. It's not the main focus of the test, but there probably will be one question on the test that has to do with limits at infinity. Main focus of the test, of course, is differentiation rules, finding tangent lines, that stuff. There will be some limit stuff though, and at least one of those limit things will be a limit at infinity. All right, moving forwards. Let's see, 1, 2, 3, 4. So what did we just do? That was 44, right? Yeah, okay. So now we're going to go to homework 5 and look at 21 and 28. Yeah, this is a good problem. Number 21 here is fun. We want to find the derivative of the square root of x over x plus 1. 14 questions on the test. Yeah, no problem. So how do I find the derivative of this square root function? It's not just the square root of x, it's a composite function. So what rule do I need? Anybody help me here? We will eventually need a quotient rule, but there's sort of something before the quotient rule. Okay, fair enough. We're going to need a power rule too, but there's sort of a, when I look at this function, I see a composite function, right? That's the main thing I see here. I see an inner and an outer. So while it's true that we are going to need both quotient and power rules, the main thing that's going on here is a chain rule. Yeah, my inner function is x over x plus 1. That's the thing that we might call u. And my outer function, f of u, is just the square root of u, which is u to the 1/2. And that's where our power rule thing is going to come in. But yeah, so really what we're going to need is a chain rule. And then it's true that to differentiate the outer function, we'll use a power rule. And to differentiate the inner function, we'll use a quotient rule. But sort of the strategic thing that we need, the thing we need to set up in our brain first, is the chain rule. So this function is really x over x plus 1, all being raised to the 1/2 power. And remember your order of operations, PEMDAS, right? Parentheses, exponents, multiplication, division, addition, subtraction. So this power is really in charge, right? This is my outermost thing. And I can't like distribute it or do any nice shit with it because the order of operations says, no, 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 you can't. Like, it doesn't work like that. I could give the power to the top and the bottom and then attack with the quotient rule. You could give the square root to the top and the bottom and attack with the quotient rule, but you're still going to need a chain rule when you differentiate the bottom function there. So it really doesn't make sense. Well, it makes sense to attack this as a chain rule problem overall. Y prime is d dx of x over x plus 1 to the 1/2. So I'm differentiating this whole function. And the way we do that is we kind of forget about the inside for a minute. You pretend like it's just a power function. You differentiate the outer function, leaving the inside alone. My outer function is this power function. So I'll have 1/2 times the inside left alone to the negative 1/2. Differentiate the outer, leaving the inner alone, and then multiply by the derivative of the inner, like this. Is everybody comfy with that? Here's the derivative of the outer with the inside left alone, right? If you differentiate u to the 1/2, you get 1/2 u to the negative 1/2. The inside is left alone. And then I multiply by the derivative of the inside. And now here, to do my derivative of the inside, this piece requires a quotient rule. So the first piece here is done. I'm not going to mess with this anymore. You could simplify it algebraically a little bit, but not much, and I don't think it's really worth it. But over here, I need to use the quotient rule to get my inner derivative. So remember the quotient rule. If I have u over v, and I want to prime all of that, that's low d high minus high d low over low low. So that's v times u prime minus u times v prime, all over v squared. That's the quotient rule. So bottom times the derivative of the top, that's x plus 1 times the derivative of just x, I'll write it like this for now, minus top times the derivative of the bottom, all over the bottom squared. And now I just have to compute each of those little primes. And that's not too bad. This is 1/2 x over x plus 1 to the negative 1/2 times. The derivative of x is 1. So this first piece is just x plus 1 times 1, which is just x plus 1, minus x times the derivative of x plus 1. Well, the derivative of x plus 1 is also 1. And then all of this is divided by x plus 1 quantity squared. What's going on here? This piece right here is just 1. This piece is 1 plus 0, which is also 1. These x's will eat each other up. And you got 1/2 quantity x over x plus 1 to the negative 1/2 times 1 over x plus 1 quantity squared. As the x's eat each other up like that. A fair question would be, can you clean this up anymore? And an answer would be yes. Yes, you can. It is possible to get the x plus 1 from this piece to interact with the x plus 1 from this piece, but it's fairly complicated. This piece is 1 over the square root of that thing. So the only way to really clean this up, you could write this as 1/2 times 1 over the square root of x over x plus 1 times 1 over x plus 1 squared, like this. And cleaning it up from here is honestly pretty complicated. I wouldn't try. All right, so I would advise stopping here. There's really no reason to try and go this far. I mean, and it's possible, yes, you can flip this upstairs. You can put the 2 downstairs, you can put the x plus 1 downstairs with the root x, and then you can get like root x plus 1 over x plus 1 squared, and there is some stuff you can do there, but it's not pretty, and I don't think it's worth it. So I would say just get to here. Questions on this one? Hammy, stop whining. Be good, bud. Sorry, my dog is being a little bit ill-behaved. Oh, no questions on this? We're all super comfy with this hyper-complicated chain rule problem? Okay, dope. Moving on. So this was 21. 21 and 28. Okay. Yeah, this is good. I like these sort of problems. It's often the case that something kind of like this shows up on my exam 1, where rather than giving you all of the pieces explicitly, you have to kind of work with a slightly more abstract thing. So here they tell us h of x is the square root of 6 plus 5 times f of x, like this. And they tell us f of 3 is 6. They tell us f primed of 3 is 2. And they say find h primed of 3. Okay, there's a couple like this. The graphing one below is kind of like this. There's one elsewhere that has something like this with sines and cosines. The challenge, of course, is I don't know what f of x is. If they gave me the whole formula for the function here, I could say, yeah, I'm just going to differentiate this. Oh, Simon asks, any preference between prime and ddx notation? I don't care. Use whatever you're comfy with. Just make sure you're using it correctly. But no, I have no preference. One way or the other, whatever you guys want is fine with me. And you can switch back and forth. Feel free to get creative. Just make sure that you are correct. So the trick here is going to be differentiating using the chain rule. And anytime we need f primed, we just write f primed. Sure, I don't know what it is, but we can work with it symbolically. So this h of x, remember, this is the same as 6 plus 5f of x, all raised to the power of 1/2. So h primed of x, this is going to require the chain rule. The outer function here is the 1/2 power. So I'm going to differentiate that, leaving the inside alone. There's taking the derivative of the outer, leaving the inner alone. And now I have to multiply by the derivative of the inner, which I'll just write like this with the prime. Is everybody comfy with this step? This is the chain rule. I used a little power rule inside my chain rule here, of course, to take the derivative of the outer, but really what's going on there is the chain rule. Now, in order to clean up the second part, the derivative of this 6 here is 0. He's just a constant floating around on his own. And then here I have 5 times f of x. The derivative of 5 times f of x is 5 f primed of 5 f primed of x. So that's what my derivative looks like symbolically in terms of the function f. Now they wanted h primed of 3. So let's say therefore h primed of 3 is what I get when I plug in 3 for x everywhere here. That's going to be 1/2 times parentheses 6 plus 5 times f of 3, all to the negative 1/2 power, times 5 f primed of 3. And now I go, oh, well, I have no idea what f of 3 is. I have no idea what f primed of 3 is. Wait, yeah, I do. That's what they told me at the start. So f of 3 is 6, and f primed of 3 is 2. So this piece is 1/2 times 6 plus 5 times 6 raised to the power of negative 1/2, all multiplied by 5 times 2. And that's the information they provided at the start, coming back to help us out. And this we can probably clean up a bit. 6 times 5 is 30, plus 6 is 36. This is 36 to the negative 1/2 power, times 5 times 2 is 10. 36 to the negative 1/2 might be worth writing off to the side. This is 1 over the square root of 36, which is 1 over 6. This is 1/2 times 1/6 times 10. which is 5/6. All right, the 10 and the 1/2 make 5. 5 times 1/6 is 5/6. There's other ways to do it, but that's the fastest. So this is a good problem. And again, you know, something like this where you have to work symbolically is likely to show up on the test. Questions on this guy? Okay, so that was number 28. 21, 28. So we can look at numbers 4 and 20. Let's see, did we already look at those? I think we might have already looked at those actually. Homework 5. Oh no, okay, but 4, so I'll set this up. We did do this in class, but I can't remember if I did this with your class or the other class. I know I did this with my other class at least twice, but I'll show you how to set up number 4 here. The challenge is that you've got 3 functions multiplied, right? Your normal product rule tells you how to differentiate 2 functions multiplied, but it doesn't tell you how to differentiate 3 functions multiplied. But you can break it down into 2 pieces. So I would break it down like this. You could break it down other ways, but you know, this is just the first thing that comes to mind to me when I see this. And then we use the product rule. And we're actually going to need the product rule twice. Product rule says u times v, all primed, is u prime times v plus u times v primed. So the derivative of my function here, f primed of theta, is going to be theta cos theta all primed times sine theta plus theta cos theta times sine theta primed. You see what I'm doing here? Every time I write this out in the prime notation without actually taking the derivatives, I'm making a plan, right? And when we make a plan to take our derivatives, we're able to take these really complicated things and break them down into simpler and simpler and simpler steps. It's the only way to do this shit. If you try to do it all at once in your head, doomed. Absolutely. I would be doomed. Anybody, no matter how long you've been doing this, is doomed without making a plan. So this is our plan. It's based on this rule. And we had to start by splitting up our function this way. I've got a piece here that I call u and a piece here that I call v, and I've got the product rule that tells me how to take derivatives of things that I can think of as u times v. I differentiate the first one, leaving the second one alone, and then I add that to what I get when I leave the first alone, and I differentiate the second. Now in here, I need another product rule. Right? This is a little u, and this is a little v. That's the challenge of this problem. Because you've got 3 functions instead of just 2, you need 2 product rules. So theta cos theta, if I want to prime that, I'll differentiate the theta, leave cos theta alone, then I'll add that to theta left alone times the derivative of cos theta. All of that was being multiplied by sine theta. And then all that's having added to it theta cos theta times the derivative of sine theta. And now I have everything written out in my prime notation. I'm ready to actually take the little derivatives. Derivative of theta is 1. So this first piece is cos theta. Derivative of cos theta is negative sine theta. So theta times negative sine theta is going to make minus theta sine theta. Now this guy is still here. Plus. Here I've got theta cos theta just chilling. And I've got the derivative of sine theta. So this is theta cos theta times cos theta. And you could stop here if you wanted to, but there's a meaningful amount of cleanup that can happen. When I distribute this sine theta, I'll get sine theta cos theta minus theta sine squared theta. And then this is plus theta cos squared theta. And you could leave it like this. This would be fine, or you could factor out a theta from the back two pieces if you wanted, but it's not really worth it at this point, unless you know some double angle stuff and you wanted to rewrite these as double angle identities, but we won't worry about that right now. This is good. Questions on this? Okay, let's look at number 20. What's next? We want to find the derivative of f prime of t, where f of t is 8t sine pi t. This is a little product rule, and within the little product rule is a little chain rule. So f primed of t here is d dt of 8t times sine pi t. And again, I'm going to come up with a plan. Thinking of this as u, and this as v. I realize that I need to use the product rule, and I'll get u primed times v plus u times v primed. And we write it out just like that. And then we see if there's anything else we need to kind of plan for. Over here, this is going to be a little chain rule. The inner function is pi t, the outer function is sine. So we will need to be a bit careful here. Over here, this is an easy derivative, the derivative of 8t. So we can go ahead and get started. The derivative of 8t is just 8. So this is 8 times the sine of pi t plus 8t times the derivative of sine pi t is a chain rule thing. This is cos pi t, differentiating the outer, leaving the inner alone. And then we have to multiply by the derivative of the inside, which I'll just write schematically like that. This is the chain rule. Here. And overall, we get 8 sine pi t plus 8t cos pi t. The derivative of pi t is just pi. And you could, because these are all multiplying, you could put the pi over there with the 8 if you wanted. You call this 8 sine pi t plus 8 pi t cos pi t. So we started with a product rule. then within our little product rule, we needed a chain rule. And we see this a lot. Questions on what we did here? Okay, we're going to go back to homework 2 then and look at numbers 31 and 42. Let's see where we are. No, don't sign me out. Homework 2, 31, 42. Okay. So this is a fun problem. We want to talk about continuity. We need to explain why this function is or is not continuous at any place. So the function down m of x is the square root of 1 plus 2 over x. Why is this continuous everywhere? Not everywhere, but why is it continuous everywhere in its domain? Well, it's not a polynomial, right? There's square roots with variables inside, so it certainly isn't a polynomial. It's also not a rational function. Again, square roots with variables inside. Rational functions are ratios of polynomials. But this does have an inner and an outer. The inner function here, u equals 1 plus 2 over x. And the outer function here, f of u is the square root of u. So it's a composite function, right? This looks like chain rule stuff because the chain rule is how you differentiate composite functions. We're not differentiating, but m of x is f of u of x is a composite function. The inner function u of x equals 1 plus 2 over x. This is the same as x plus 2 over x. That's a rational function. So it is continuous everywhere in its domain, which is negative infinity to 0, union with 0 to infinity. Sorry, let me get this out of the way. Ah, no, God damn it. So he is continuous everywhere in his domain, which happens to be all real numbers except 0, because that's where the bottom is 0. The outer function f of u is root u is continuous everywhere on its domain. It's a power function, and its domain is the left closed, right open interval 0 to infinity. So you take two continuous functions and you compose them. We know that the composition of continuous functions is continuous. So m of x, which is f of u of x, must be continuous everywhere on its domain. Now, the last thing we need to do is actually find the domain of this function. The domain of the inner part is everything except for 0. And the outer part is happy as long as the inside is greater than or equal to 0. So to find the domain, we must solve the inequality u is greater than or equal to 0, which is the same as saying like the inside of my square root, right? We called the inside of this thing u. If you didn't want to call it that, you don't have to, but you called the inside of this thing u. We need to figure out where the inside of the square root is greater than or equal to 0, because you can't take the square root of a negative. So you say 1 plus 2 over x is greater than or equal to 0. Inequalities like this, so-called rational inequalities, are hugely important in this class, important enough that if you look back in your modules, I actually have a few links in the review material for solving rational inequalities. Look here. You see solving inequalities here. And then there's another one on solving rational inequalities, specifically rational inequalities down here, polynomial inequalities down here. These are things we need to be comfortable with. So what we're doing is we're trying to find the domain of this function m, trying to find the domain of this thing. We know right away that x is not allowed to be 0 because there's an x downstairs here. But we also know that the square root isn't going to be happy if the thing underneath the square root is negative. So we need to figure out where the thing underneath the square root is greater than or equal to 0. That is what will determine our domain. And the way you do this, you should follow those links that I posted if you haven't seen this in a while, if you forget. But the way you do this, first you have a common denominator. You pull everything to one side, you have a common denominator, and then your special numbers will be places where the top or bottom is equal to 0. So those are 0 and -2. You plot them on a number line. And then you test a point from each region. We could test x equals -3. And we get -3 plus 2 over -3. This is -1 over -3, which is positive 1/3. So this function is positive over here. We could test x equals -1 in here. -1 plus 2 over -1 is 2 over -1 is -2. So my function is negative in here. And over here, you could test +1. I'm just plugging into this inequality here. -1 plus 2, +1 over 2 over 1. That's 3 over 1, which is 3, which is positive. So my function 1 plus 2 over x is greater than or equal to 0 on the intervals -∞ up to -2, and that's going to be a bracket union with 0 to infinity. I can't include 0 itself because it makes this thing undefined. I can include -2 because this thing makes -2 makes the top 0, and 0 over -2 is greater than or equal to 0. So again, if you're rusty on solving these rational inequalities, you might want to brush up on it before this test. You will definitely need to brush up on it before the second test. The second test will have lots of inequality solving like this. This first test, not so much, but here we go. So our domain is all the stuff that makes this happy together with all the stuff that makes this happy, which is just this set. So this turns out to be the domain of M. And that's the whole problem. So we can use those theorems to argue that this function is continuous everywhere on its domain. And then we find the domain by making sure we stay away from any problem spots. The problem spots would be places where the variable downstairs is 0. Right? So that means we got to stay away from 0. And also anywhere the thing under the radical is negative. So we set this thing greater than or equal to 0 and solve that, and also make sure we stay away from x equals 0. And that is going to be this set. Okay. Where are we here? Let's look at number 42. That's probably next, right? Is that, yeah. Okay. This one's not super fun. You just need a calculator. This is not a sort of problem I would put on a test, but they're asking you. So let me try to show you why this problem is worth including. One minus 4 over x to the x. They say estimate then x to infinity f of x. To a couple of values, right? To, what was it, like 2 decimal places and then to 4. Yeah. So this is a question that's assuming you're using a graphing calculator. And what they mean is that if you come in here and type this guy, like this, you can then use the graph to estimate the limit reasonably well. You can use a table to estimate the limit to 4 decimal places. But why is this interesting? Before I do this, what makes this limit hard? Well, the limit of the inside this would be 1 minus 4 over infinity. What's that? Pull back some interaction here. Yeah, what do we got there? Yeah, this is 1 minus 0, which is 1. But overall, we have lim x to infinity 1 minus 4 over x all raised to the x. So this kind of looks like, I'm going to put this in quote bunnies to say I don't take responsibility for this. This is like 1 to the infinity. Which you might think is 1, but this is actually an indeterminate form. If the base was actually 1, if it wasn't like going to 1, if the base was constant 1, then this really would be 1. But the base going towards 1 and the power going towards infinity are fighting each other. So this is actually a very hard limit to take. We cannot calculate this limit just by plugging in, even using the theorems that tell us like 4 over x goes to 0. Because then I get like, okay, 1 to the infinity. Well, what the fuck is that? Turns out I can sculpt this to be any number you want. This particular guy is going to e to the negative 4, or 1 over e to the 4. And I'll show you how we can figure that out, but it's going to have to wait until we have L'Hopital's rule. So the idea is that this is actually a hard function to work with. This is challenging because the base isn't constant and the power isn't constant. So it's a difficult limit to calculate. But if we use a tool like this, fuck with my window settings a little bit here, and change these to 100, and then we'll look at the graph. I need to Yeah, my window settings, sorry. We're not gonna be able to see that with that Y scale. Y min, let's just go 0, 0. Y max, let's call this 1, and take Y scale 0.1. Maybe now we can see something. It's still too small. Yeah. So even if we were to like, play around with this a lot. There you go. You can kind of see it. And then if you hit the trace button, you can sort of bounce as far out here as you want along this graph and try to guess the first few decimal places. So it looks to me like the first 2 decimal places are probably 0.01. Something like this. I should say approximately. And then 4 decimals, they want us to use a table. The way we would do that is you hit second graph. This doesn't really matter for us because you guys aren't allowed to use these calculators. And certainly you won't be using them. I would hit actually table set delta table. Let's start this at 100 and take step sizes of 100 just so we get out there quickly. And come back to our table function. There you go. We're just blowing through these things now. If we come way down here till we really trust we have those first 4 digits safe, I'm thinking they probably won't change much after this. This looks pretty safe. We're all the way out into the 10,000s now. Yeah, probably 0.0183. Now, if you want to know what's actually going on here, we can graph this in Desmos. Scales might not be too bad for this, actually. And it's trying to give me some values that correspond to, yeah, very, very small y values here. So 0 to 0, 0. There we go. My x-axis way out here. All right, so you see, this is actually a pretty interesting function. Very strange function. And if you want to know what this is approaching, it's this. But it approaches it very slowly. And I'll show you how to cook this up down the line. You're not expected to know this right now. But yep, that's the game here. And this red graph is indeed sneaking up on this black dotted value, which is e to the -4. But yeah, for now, it's just a calculator exercise. Nothing like this will show up on the test, I promise. No calculator exercises because no calculators. Just so we're really clear on this, the only calculator you guys are allowed to use is the TI-32XS or TI-30XS2. No pros, no 36s, certainly no 89s or 84s, no graphing calculators at all. So a question like this, I would not put on the test. But it is an interesting thing to explore. And the reason it's interesting to explore is because you come up with this 1 to the infinity thing. And it's like, well, what the fuck is that? Shouldn't that be 1? But the base isn't always 1. It's just very, very close to 1. So you've got something very, very close to 1 being raised to a very, very large power. You might think that that will always come out to 1, but it doesn't. The power and the base are fighting each other. And they fight each other in just the right way that you get something interesting out. It may also be worthwhile to recall the normal definition of E. E is normally defined to be the limit as x goes to infinity of 1 plus 1 over x to the x, right? This is how you define E. In pre-calculus classes, college algebra classes, we say it's what this goes towards as x gets bigger and bigger. So it's not surprising that something like this is related to something like this. Okay, let's see how we're doing on time. 12:16, we are right at time. So I am going to have my normal office hour this afternoon. I'm also going to post this and last Friday's video. I know I haven't posted that yet because I've been busy moving. So between now and the office hour, I'm going to move very quickly to get those posted. And then I will upload those and have my normal office hour. I really don't have time to talk much after class today, but you can watch the video. I'll have it up on YouTube in just a minute. Katie, also, if you look in the announcements for our class, you will find everything you need here. So one of them, here's the announcement with the rules for the test, right? All the instructions for the test. And down here, where is it? Do I have the study guide? Oh, no, you guys don't have an announcement for the study guide. So if you're wondering, Katie, how do you write out your study guide problems? It's not a big thing. Just scan the work for your study guide, whatever work you used as you solved the problems, scan that work and submit it to the assignment under study guide 1 in Canvas. Make sure you have a solution for every problem and just write like you would on a test, right? Write out your work and I'll get in there and make some comments and that'll help you get a feel for how I'm going to grade the test. Yes, Karen, if you submitted your study guide before today, like by the start of class today, I will be going in tonight and making comments on those. So I won't be making a lot of comments, but I will make comments on at least a few problems to help you get a feel for how I think your notation is and if you need to change anything. So as long as you got it in by today, I will get in there and make some comments for you tonight. Any other questions, guys? Or anything else that at least can't wait till office hours? Okay then. All right, I will either see you guys in office hours or next, next class time. Remember the next class time, please just read this announcement. We'll be signing in and saying hi to each other on Zoom on your phones before you start the class, and then we'll get everything set up for the proctoring. It'll all go well. Okay, that's it. If you do have any questions or any concerns, reach out to me. Office hours would be best. I know I'm backlogged on email. I'll be getting through as much of that as I can today, but things are just a little bit hectic right now. So if you've got urgent questions, office hours are best. That's it. I'll see you guys either in office hours or at the start of the test on your phones on Wednesday. Take care.